Hello and welcome to another video on orbital mechanics. I'm up to problem 2.43 in the book Orbital Mechanics for Engineering Students by Howard D. Curtis, 4th edition. And I was just doing this question, but my storage ran out and then I just decided to record it again from scratch, but I didn't want to write it all down again. Anyway, the question is, at a given instance, a spacecraft has the position and velocity vectors r0 equals 7000 I and b0 equals 7I plus 7j relative to an Earth-centered non-rotating frame. So here is our point here, our spacecraft. Here's our focal point, and here's the 7000 r0 that is provided. So we're just going to do that as across as x, and then it says that the vector velocity is 7I plus 7j, which is 45 degrees because they're both the same. So we can just say that's our velocity, and this is our probably what our orbit looks like. And in order to work this out, we're going to use the Lagrange coefficients initially, and that is one of the, as you can see in my previous video about Lagrange coefficients, go watch that if you haven't. F and G are defined as such, and R is defined as such here. For more details on deriving these, which are not difficult to derive, they're just fiddly, these are designed to be in terms of delta theta, not in terms of the initial position and the final position, but in terms of the change, which is why they're useful. But R, which in this case is what we're actually looking for, is defined as this, and it would also give us our coefficient. So when you work all of this out, you will get R to be 43,183 kilometers J, which, because it is, well, what is the position vector after the true anomaly increases by 90 degrees? That's the question. And that is 90 degrees there, so we can imagine that we're going to end up vertical because we were horizontal here, so we're going to end up vertical here on the paper. So it's, only in terms of J. So that's a good indication that it's correct. And so that is the position in the end. So it also wants what is the true anomaly of the initial point. So this coefficient business doesn't give us the angle at the initial conditions. So we're going to have to work that out the old way. And we first want to confirm what type of orbit it is. So we want to check the energy. So is energy less than 0? Yes, it is less than 0. That's our equation for energy. And if it's less than 0, it's an elliptical orbit. So we can use the semi-major axis equation like this. And we can use the eccentricity equation like this. And that will give us those values. And then we can plug those into any of the angle formulas you like that take all these values. The one I use here is just h squared over r mu minus 1 divided by eccentricity. And that's just me rearranging one of the equations, and that gives 99.21 degrees. So yeah, to be honest, this coefficient stuff is not that useful in this case because it would have been easier just to go and find the initial and true anomaly and then use that to find the next position. So there's other ways of doing this, but this is just to demonstrate the coefficients a little bit. Anyway, that's 2.43. I'm just going to flip over and do 2.44. Yep. So 2.44 is very similar. Relative to an Earth-centered non-rotating frame, the position and velocity vectors of the spacecraft are r0, which equals 3450 I minus 1700 J plus 7750 K, and velocity naught equals 5.4 I minus 5.4 J plus 1 K. It's all in kilometers per second. And it says find the distance and speed of the spacecraft after the true anomaly changes by 82 degrees. So a little bit better to use the coefficients, but we also don't have to. We could do this by finding the eccentricity, but we will do it by finding the Lagrange coefficients. So yeah, as we saw, F is 1 minus mu r over h squared upon 1 minus cos delta theta. This one isn't asking us for the initial angle, so that's good. G equals r naught over h sine delta theta. F dot equals mu over h 1 minus cos delta theta over sine delta theta upon mu over h squared from 1 minus cos delta theta minus 1 over r naught minus 1 over r. So a bit long-winded, that one. And then g dot equals 1 minus mu over r naught over h squared from 1 minus cos delta theta. Yeah, and we need r, and r is equal to h squared over mu 1 over 1 plus h squared mu r naught minus 1 cos delta theta minus h radial velocity naught over mu sine delta theta. So should be able to get radial velocity by now. That's just a component of that. Yeah, we need to project that velocity onto the radial vector, which is, so VR equals, and the projection is V naught dot R naught over, sorry, when I do vectors, I want to make them capital, over R naught, and when they're magnitudes, I'm in lowercase. So that gives you the velocity radial in the direction of the radius vector. So now we've defined everything there, and we can get everything, and we have everything. Well, h is R naught cross V naught, and then h is the magnitude of that. And then once we have these four coefficients, we're saying that r equals f r naught plus g v naught, and v equals f derivative r naught plus g derivative v naught. And when you work those out, it's asking for the magnitudes, distance and speed, so we're not looking at the I'm not going to put down the vector, so it's going to be 19.266 kilometers here, and sorry, yeah, 2.925 kilometers per second. I'm going to put all of the MATLAB scripts in the comments, in the description. It also says verify that specific angular momentum and total energy are conserved. So what we can do here is just say F times G derivative minus F derivative times G equals 1. We just check that that equals 1, and it does, so that confirms that the energy, the angular momentum, is conserved. And if we also check our energy, so we'll just do E equals V naught squared over 2 minus mu over R naught, and we'll do E 1 equals V squared over 2 minus mu over R, and you'll see that these are the same, right? These are, what do I get? Minus 1.641 by 10 to the 7. So that confirms that they are matching. 2.45 actually is asking something that isn't actually done in the book yet. It's asking about time. So I'm going to come back to 2.45 after we've done a bit more, done some of chapter 3. Okay, so that's that. If you have any questions or you think I've made a mistake, leave them in the comments. Thank you. Goodbye.